In the first part of the course, most of the systems that we're going to be considering are systems of gases. And so when we talk about gases and we want to define the state of the system, it's going to be very important for us to define the pressure, the volume, the temperature, and the amount for these systems so that we can really specify their state. Now, what would be even more important for this is if we can define an equation that relates these to one another, because we know intuitively that if we change the pressure, that has an effect on the volume and the temperature. Or if we change the temperature, it's going to have an effect on the pressure and the volume. So what we need, if we can get it, is to devise some sort of equation, and we're going to call it an equation of state, that specifies how all these properties are connected to one another. Now we might write that abstractly as some function that is a function with these as its various variables, and we're going to say equal to 0. I mean, we could say it equal to a constant, but if it's not equal to a 0, then we could just say it's minus a constant equal to 0. All right, so what we want to do is figure out what is that equation, what is that function that we've written there. Now, in order to get a handle on that, we're going to go back and look at the results of some experiments that were done back in the 1800s. And what they did was to derive what we'll call empirical relationships between these various properties. And they're, of course, so famous that they put them in general chemistry books, they put them in physical chemistry books now, but we're going to tack them one at a time and see what they add up to. Now, early on, one of the very first was looking at the variation of volume with pressure, holding temperature and amount constant. And what was found at the time was that volume was proportional to, that little symbol means proportional to, 1 over the pressure, and that's with constant temperature and amount. And what that looks like when we graph it is a curve that looks something like this. All right, or we could also write PV equals constant. This is the same thing, and that constant depends on what constant values of the temperature and amount that we chose for that. This was a law that was originally discovered by Robert Boyle in England. So it's sometimes called Boyle's law. And if you want to imagine what this might be like, imagine if you had a piston in your hand and it has a certain amount of gas in it that you're holding constant and it's at a certain temperature. If you were to press down on that piston, you would be increasing the pressure, and in increasing the pressure you would be reducing the volume, and it turns out that the volume goes inversely proportional to the pressure. Now we could also do a similar thing when we look at volume and temperature, and we find that in fact volume is directly proportional to temperature, again with constant pressure and constant amount. So it's going to look something like this, just a straight line with a positive slope. And in this case, the equation that it's implying is something like volume divided by temperature is constant. And this was a law that was discovered independently by a couple of folks, by Charles and by a French scientist, Gay-Lussac. And it's another one that's, I think, pretty easy to understand. If we increase the temperature, let's say we blow up a balloon, it's got a certain fixed amount of stuff in it. The balloon is at atmospheric pressure, the pressure of the atmosphere around it, and it will stay at atmospheric pressure. If we heat up the air in that balloon, it will expand. Likewise, if we cool it down, it would shrink. If you've ever lived in Minneapolis in the wintertime, you might have experienced this with your car tires. They actually get smaller during the winter because of the cold weather. Finally, we might look at how the volume changes as we change the amount. Well, this one again is very easy and very intuitive. It's proportional to the amount. So again, it's a linear relationship that looks something like this. And we can express that as volume divided by the amount is a constant. This was a law originally determined by Avogadro, an Italian chemist. And I should have written the labels on the axes. So we have these three empirical relationships that have been discovered over time, and let me summarize them over here, and I'm going to draw them in red because we want to highlight these. Volume is proportional to 1 over pressure. Volume is proportional to temperature, and volume is proportional to the amount. So if we want to combine all of these things together into one law that sort of connects all of them together, then we might say that volume is proportional to the amount times the temperature divided by the pressure. That would be a way of combining all these equations. Now, it's proportional to, and the way we can turn this into a real equation is by inserting a constant. And so in this case, we would insert the constant R. And so this would be an equation that relates these different quantities to one another. And this R is something we call the gas constant. And you're probably familiar with that already, having seen it in various contexts. So what this would imply is that our equation, our F, our function of pressure, volume, temperature, and amount, is now just equal to pressure times volume minus amount times R times T is equal to 0. Or maybe more familiarly, we've seen this written as the ideal gas law, or I'll write it over here, PV is equal to nRT. And it is more formally called the ideal gas equation of state. So it is an equation of state that relates all of these various properties to one another, and very useful in that way. Because it's particularly simple, we're going to use it a lot in our examples, and eventually it'll take us several weeks, but eventually we'll get to non-ideal gases, but for the most part we're going to be talking about ideal gases. Every gas is ideal if it is dilute enough. That is to say, its particles are far enough apart, it's not interacting very strongly. Now, one of the things that I haven't answered yet, and that is the value of this gas constant, R. Now, when you saw this first, probably in general chemistry, you probably saw that R had a value that looks something like this. 0.8206, or you can go on out. If you go to Wikipedia, you can find a whole bunch of digits for R. In fact, we can just keep going here. It's equal to a lot of stuff, but 0.08206 is probably the form you've seen, and it's in units of liters times atmospheres divided by moles Kelvin. All right. It's important to specify the units when we talk about R, because if we use different units, R is going to have a different value. For example, if we have pressure expressed in bars, then the value for R is going to be 0.083144 and so forth. And now the units, instead of being liter atmospheres, they're going to be liter bars per mole Kelvin. All right, so we always want to specify what units we're expressing pressure and other things in so that we can get the value of R correctly. Now I want to, let's go to a fresh page. I want to talk a little bit more about the difference between bars and atmospheres, because I just sort of threw that out last time. Why do we use bars instead of atmospheres? Well, remember that pressure is basically a measure of force per unit area. So if we were to put this purely in the metric system, then the force would be newtons, and the area might be something like meters squared. All right, so when we express it this way, and if we write out newtons for what they are as kilogram meters per second squared, this is going to be kilograms per meter second squared. And this turns out to be now a unit of pressure that for the metric system that's called 1 Pascal, named after Blaise Pascal. All right, so the Pascal is actually the unit that we probably should be using for pressure, but it's a really tiny amount of pressure. So if we were to actually express atmospheres in terms of pascals, we would find that 1 atmosphere is equal to 101.325 kilopascals. That is 1,000 pascals. So it's 101,000 pascals, all right, which is a lot of pascals. That means Pascal's even smaller than a torr. And it's just not a very convenient measure of pressure for us to use for systems that are roughly near an atmosphere. Now, I'll point out something else, and that is that newtons when we use the metric system, newtons are also equal to joules over meters. So if a Pascal is equal to a Newton per meter squared, and a Newton is equal to a joule per meter over meter squared, then this is a joule per meter cubed. Okay, now it's getting very suggestive here. So what we have really is that pressure is a measure of energy divided by volume. All right, interestingly, that means that the product of pressure times volume is really a unit of energy. And that's useful to know because when we write down the ideal gas equation, we don't often think of it this way, but what we're really writing down here is an expression that relates energy of different forms in our system. Mechanical energy in terms of pressure and volume, and heat energy in terms of the temperature of that.